Hello everyone. I hope all of you can see me now and hear me now. And welcome to the events of EPAM Z Nights. As the first presenter, I'm going to give you an overview of different kind of health check patterns. We are going to compare them to each other. Going to have a little demo at the end. Um, my name is Oresztesz Margaritisz. I work as a chief software engineer at EPAM currently. Um, Immediately, I would like to start with a little bit of exercise with all of you. So, I assume that each and every one of you are able to actually recognize the symbols of the screen, especially those people who already have a driving license. Most of them actually, to give you a simple summary, even if you don't know the concrete um, issue of appearing in your car or happening in your car, most of them just simply means that there is some trouble inside your machine, and it's better to visit a car mechanic so they can fix the problem for you. All right, so car manufacturing already knew that their system is not perfect. It doesn't mean to be working 100% all of the time. That's why they built in this functionality to actually handle failures in a way that maintainers and users can just safely recover from these. So why my question is that why would software be different, right? Maybe some of you has the feeling that um, because my code is represented as a static text, because I can just simply figure out what's going on step by step by a debugger. It's also being executed the same way during runtime, but this is not true. Runtime is a dynamic environment, so this means that because you are introducing different kind of dependencies and interdependencies that nobody expects, it's going to behave very differently in different kind of scenarios. But first question you might have is that how serious or severe is the problem? That's what, for example, my first interest was when I was investigating this topic. So what you currently see on the screen on the right side is the so-called reliability curve. There is a theory behind the reliability curve. It's enough for you for this time to just understand that it shows you the still non-faulty, still running components of your system versus all of the components, even the failed ones over time. And what you need to remember from the story is that this is an exponential curve. So this means that at the first very short period, you will see a few or one of your components introducing some kind of failure or providing some kind of failure. And soon after, what will happen is that majority of your components will also have various kind of failures. And again, pretty soon after comes total blackout. And again, what you have to remember from all of these stories that this is an exponential curve. So things are happening very fast. So if you were thinking about a strategy like let's introduce maintenance in the next sprint, if your next sprint is happening within a month, that means that you have to actually deal with outages soon, very soon after your first release, and you cannot wait until a month until you introduce these kind of maintenance features in your code. All right. Another fact that we need to deal with is that you cannot build up 100% available system based on not 100% available components. Again, this is just the facts coming from simple statistics. What you can see on the screen is just a simple schematic of a working computer. Okay, now let's say that, in theory, let's say that each component has 99% of availability. It might be more in reality, but let's say that it's just like that. So this gives us a graph of dependent component, and the total availability just simply can be counted, and it's just going to be 96%. Now, nowadays and today's in the world of microservice, there is no such architecture as single instance architecture. That's the fact. So, so that means that usually you have something like what you have on the screen. You have a client talking to a server, talking to a database, right? So what happens when you increase the complexity just simply adding three machines that are dependent of each other? Again, let's assume that all of the availability of each individual element is just 99%. Now your availability just dropped down to 88.5% just because you introduced much more dependency in this architecture. So what this means for us again is that things go south very easily. All right. Probably that's why IT team looks like before they are going on holiday. And not just because um, the machines that they are using are not reliable, not just because the network cables have some issues needs to be replaced and so on. It's also because your code is running on these machines, and these guys know that, and they're more experienced than you. So if we are look at just a single instance of running code, we can experience different kind of issues like simple bugs. That's something that's unavoidable, unfortunately. But you have to deal with different kind of problems like configuration issues. So assuming that this is something that's not cannot be tested, and assuming that in production, when you deploy to production, that's going to be the first time when you are going to test your configuration if you change something. All right, there's no way to test this out with just unit testing or integration testing or everything else. You also need to deal with different kind of synchronization issues that might just be familiar with for you as inconsistencies, different kind of memory leaks and thread leaks, and unfortunately pool misconfigurations. So again, I assume you that most of you, because the lack of time, has not been reviewing their connection pool or dependency pool configurations. Not all of them, and not all of them are fine-tuned. Okay. And as the last typical cause of outages, there are deadlocks, not because just because of your own code. It can be introduced in a library or dependency or anything like that, or maybe the HTTP server that you are currently using. It's it's unpredictable. These are unpredictable outages happening all the time. All of them has different kind of characteristics. All right. So how do we deal with these problems? Usually, the easiest way to introduce fault tolerance is to introduce some kind of redundancy. So this means that I am going to multiply or replicate either one or two of these components or all of the components at once. So typically, if you think about data redundancy, you just copy over the same data to different kind of locations. This is, if we are talking about just a disk, this can be a RAID configuration. When if you have some data issues in one of the disk, you can still um, go out and go for the other replicated volumes and still get the valid values. Databases do this all the time with timing redundancy by saving multiple versions or storing multiple versions of the same record at the same time. This is familiar for US transactions. And again, the other most common way is to introduce, let's call them service redundancy or process redundancy, by running the same version of the same process in multiple instances or multiple machines. All right, now all of these solutions for failures, for introducing fault tolerance, introduce some kind of controller. that you can see as an orange, big orange arrow on the left side. And for this to work properly, the controllers have to know which of your instances are still able to provide or to consume workloads, which are those which can't. That's why software engineering introduced the concept of health checks. So the purpose of health check is to tell to these kind of controllers if your machine or if your process is still able to consume workload um, or not. Simple like that. Now, why simply can't we say that, okay, health checks, not a big deal, just return something simple and job's done? Of course. So I have a story for you that simply I think shows very well how health checks implementations can turn into something very bad. So in this story that I've read about recently, the developer introduced an error in the in the application code that was responsible for providing um, backend template rendering for their website. And the defect just simply caused the application to return a blank page. Now, the problem with the solution was that, first of all, it was not detectable in the health check itself because the health check was also just returning just a simple HTTP OK response. So the blank page also worked, but the other problem was that the blank page was rendering, was giving back responses much faster than the other instances which had to do some kind of work. So let's say if the response time for the backend rendering was 50 to 60 milliseconds, the blank page rendering was just 5 to 6 milliseconds, which was 10 times faster. And the load balancing before the fleet that was responsible for this kind of rendering was set to route traffic to the instances which had the least workload, which were responding faster or the fastest. So actually this new release just turned into a black hole and just sucked in all the client requests, and it was providing a real outage at the end. So I think because of these stories and because I hear these stories all the time, um, I think it's important to talk about the health check, the various implementations, and to know which one to use in which case, even though it looks like a simple topic. So let's look at the anatomy of a health check a little bit before we talk about the patterns. So as I said, health checks are usually used with some kind of controller in place. This controller just simply has to check if your application is working properly or not before assigning workloads. And based on your response, it can provide some kind of actions. Okay. When it's asking if your application is healthy or not, your application just simply tell the truth or an assumption or just simply can lie, like what happened in the previous story. Okay, so that's the two cases that we need to investigate. Are we able to avoid different kind of issues that we are talking about or not for a specific health check implementation? If we talk about the various kind of actions, we can say that you can take an action like doing the restart, for instance. You can apply some kind of traffic shaping on the cluster itself. You can configure some kind of alerting, but when you think that you cannot recover from the problem by yourself, by the controller itself, and some human needs to be involved, you can do some scaling also, um, and you can control the deployments. So that's the various aspects that we need to consider when we will talk about the implementation themselves. Okay, now just giving you a summary of what kind of patterns are we going to talk about. We have to, of course, consider the case when we don't have any HashCheck implementation. So I won't judge anybody who listens to this talk. There are some situations, let's say when you are maintaining a legacy application, when you can just simply don't have any options. So it's okay to discuss this scenario as well. Of course, we have another kind of health check called shallow health check, when you just simply return a blank page, or something, try to do something simple. Um, I think there are different kind of patterns called deep health check. When you try to investigate not just the instance itself, you try to go deeper and also give some kind of summary of the services dependencies. And we have something called the passive health check, which I've seen recently, which I think the most advanced way of providing health checks. We talk about why in the talk in various sections. Right now, there are many other fault tolerance patterns available for us. I think the most common that you know is circuit breaker, for instance. But what is the connection between health check implementation, and all these kind of other fault tolerant patterns? So let's also clarify this as well. Um, what's the situation with retries? Do I need to consider retries when I'm implementing a health check response or not? I say that you should not bother with that at all, because the next retry should happen at the next period, when the application itself or the control itself again tries to ask the health check of your application. Retries just overcomplicate your implementation, so don't include the retries when you are providing this information. Now, timeouts is something that I think is mandatory. Okay, so if your health check period is configured to 10 seconds, why go out with something that has the timeout of 30 seconds? Right, it's just going to mess up your data, your responsiveness. So dial down the timeouts for all the connection pools you are trying to report in your health checks. In this case, what I make sense is at most 5 seconds of timeout for um, for the health check period, or 10 seconds. It's um, it's fair enough, I think. In this case, you don't need to have any longer timeouts. It's not going to provide you any better guarantees. Okay, but what was the situation with other kind of fault tolerant patterns that are a bit more complex, like circuit breakers, providing defaults, providing fallback mechanisms? What's the relation with your health check implementation? And these, how I can fine tune my health check response with my circuit breaker configurations, which can be very complex. So that's problematic in some of the pattern implementations. Some of the patterns will provide you some very good relation with the other patterns. But this is something that we need to consider when implementing the health checks, and especially if you are using other fault tolerant patterns. Okay, so let's give you a summary of the patterns themselves, including some kind of comparison, some kind of guarantees of what kind of failures are avoidable with each of them. So what happens if you don't have any health check implementation? Luckily, if you have a cluster orchestrator in place, you can still have some guarantees. For instance, so if you are working with something that's monitoring your containers for instance, in Kubernetes, you can provide the number of desired instances running or the number of replicas running. And if your container exits, and if it exits with a provide in a provide in a proper way, then if the orchestrator detects that, it's going to restart them. All right. There can be only an issue if your container is just keeps up and running, even though your main process just exited, or even if your HTTP application or web application exited. So if you are working with something legacy, try to migrate into containers, at least make this test by yourself. exit the application, check if the container exits itself. Okay, for alerting, if you are working with a load balancer that's representing metrics for the different kind of response codes, like the load balancers or reverse proxies I worked with, and with the proxies I used in the sandbox, then you can provide a failure rate based on the HTTP responses. Of course, this is just available when you are handling a layer 7 load balancer, which is interpreting the HTTP request response itself also. So you can see that in Prometheus, both of the metrics are very similar. I tried to use for a failure rate the proportion of the successful response codes or the faulty response codes versus all the others. And this is the diagram that I will get at the end. Now, one thing that I want to mention when working with rates is that pay attention to the interval, because if you have just this kind of small spiky outages that's going to disappear from time to time, it won't be visible if you use a shorter or a longer period. So what you can see on the left is the same diagram from the same time period with an interval of 5 minutes. What you can see on the right is the same time period again with the interval of 1 minute. So in this situation, what happened is that the database just dropped out, and this because of this, also the services response rate was also increased. And because of the differences of this faster response rate or faster responses provided versus the slower response rate, um, this this kind of failure rate was not showing up these spikes if you have longer intervals. Okay, now I say that the risk that you are taking is that you cannot simply apply traffic shaping or deployment. If you don't have health checks, I haven't found any kind of solution to that. Another thing that needs to be considered is that you are just going to, if you have the metrics in place, at least with alerting, you are just going to catch the possible memory and thread leaks, but not the other kind of issues. Okay, so it's very, very, very limited. Now, what should we do with shallow health checks? What you can see on the screen is not just a simple HTTP 200 response. I try to include also the disk space here. So if you are doing some kind of I operation like logging, you should consider including them also in your health check, because at least you need to predict that okay, you are able to write um, some amount of data in the future. Of course, this is not perfect because many of the implementations, like the implementation that I did, and for example, the default implementation in Spring Boot, is not really writing to disk. So it's not going to avoid different kind of situations that can lead to, again, different kind of failures, like when simply just write failed. So having free disk space doesn't mean that your write is not going to fail, or when, for example, you are out of inodes and cannot create any more files, and these kind of scenarios. So it's important to mention that this is not perfect for if the IO is important for you at the same instance. But at least it's more. It tries to dig deeper and provide some more information. So, what options do we have with restarts? Now, with restarts, I can have in Kubernetes a liveness probe, and if this liveness probe just reports an issue, my container is going to be restarted. So if let's say I'm out of the disk, I have the chance to restart my container in another node that might have more disk space mounted underneath, and my overall this won't affect actually my cluster's healthiness or availability. That's the good news. Okay, Of course, again, we can do some traffic shaping. So the load balancer just simply is going to ask this kind of shallow health check, and this shows the healthiness of the HTTP pool itself. It's going to provide some information if the pool doesn't have any kind of deadlocks, or it's not depleted, or if not all the threads are blocked in the pool. But what happens in case my database is going to be down? Now the health check is just lying, because if I get some um, workload routed by the load balancer, I cannot do the real work here. So we have to consider these kind of scenarios, and of course we can have various number of connection pool issues that we need to talk about. Again, wrong timeout settings, having lots of invalid connections in the pool which cannot be checked out, or which needs to be again collected and reinitiated. Um, you need to deal with block threads if you have, let's say, a wrong pool implementation. It's not unavoidable, and it happened with me like, or at least 2 or 3 times. So it's not impossible to see these issues in production. Um, if you have an unbounded pool, again, having thousands of connections, it's not funny, especially if you have several instances, it's going to kill your CPU. And you have to deal with the scenario called overflooding, when all the instances start up from nothing and start caching and start requesting lots of things at once from the database in a big batch, and various thread and memory leaks. Okay, so not including the connection pool in this kind of health checks is again something that's not really wise. So we have to take this in our mind when choosing an implementation. Now with alerting, good news is that at least Envoy, which is again a pretty popular load balancer or reverse proxy, provides metrics for cluster health checks. So I was able to provide a diagram by the Prometheus query below. Um, it's also monitoring my instances actively when they don't receive any kind of traffic. So when traffic arrive, let's say have a warm-up period or something like that, the instances will be always checked if they can uh, provide some workload or not. So it's not traffic dependent. That's the positive thing from shallow hash checks. Unfortunately, because shallow hash check talks about the instances, usually it's not applicable for controlling deployments, because it's not providing any kind of check of the tests of the configurations that we have. Especially think about the scenario when the database goes down, database configuration is incorrect, then I cannot act on the deployment itself when it's ongoing. Okay, so as a summary, I think we are at least be able to capture the memory and thread leak, the thread leak, especially if it's happening in the HTTP pool, but of course not the other issues. Now with deep hash check, we are trying to go a bit deeper, as I said already, and try to report also some kind of information from the dependencies, like the database. So the default implementation most commonly is doing some kind of connection pool validation, running a simple query, and giving back simple responses. Okay, everything's of course everything looks good, so this is the default that we should use. But it's not true again. That's the problem. So I will tell you why. Um, the restarts and deployments now can be separated. So in Kubernetes, again, liveness probe just provides the checks if the container is live or not and restarts the containers if there's a problem. So that's not really makes sense to include um, any kind of dependency there, because if the database is not available, a container restart just simply won't help. So that's why it's good to separate liveness and readiness probe in different endpoints and to include the deep health checks only in the readiness probe. And there is another kind of feature that I advise to use. This is the startup probe. Startup probe just going to block your deployments or the container startup until it's not until the response below does not provide an HTTP OK. So it makes sense to include everything in the startup probe, because let's say if the database is not ready, then it does not make sense to just go out and roll out my deployment. What we should do is just to investigate and maybe roll back, take a step back, and figure out why what we are trying to do is not working. All right. Now, problem is deep hash check is that, again, we need a different kind of pattern or fault tolerant pattern in the load balancer itself. Because what happens if the database goes down? How should the load balancer just act on that? So should I just deny traffic of one of the instance because it's reported as failed at the other instance as well? Then I'm not going to be able to provide any traffic. So many of the load balancers have this pattern implemented called fail open. This means that if every instance is reported to be unhealthy, at least keep some traffic on the instances, because probably there's some kind of configuration issue or defect in the hash check implementation. We should not just go down with all of the cluster at once, because load balancer is not able to figure out what's the wise decision in this case. So that's why they have this fail open mechanism implemented. Okay, I said that it's important to consider different kind of hash check implementations if I have other fault tolerant patterns. So let's say again, database is down. If I'm doing traffic shaping and have some kind of fallback and defaults, does this mean that this instance is healthy? Does this mean that his instance is not healthy? So one of the solutions for this problem is using probing. That means that I should just simply ask or submit a synthetic request that goes through the same path as a normal transaction. And if it reports something that was a successful response, I can probably say that a real request will be okay. The drawback of this mechanism is that if I have a big cluster of many hash checks ongoing, that's going to skew my existing statistics or metrics, because I'm going to be full of these synthetic requests. So again, this is not perfect. At least it's able to get, because I'm going through the same request path as a normal transaction, is going to be able to capture at least the defects themselves as well as the deadlocks, and it's going to also honor my fallback default settings as well as the circuit breaker settings. So far so good. So something that's more advanced for the cost of having synthetic statistics and metrics, logs, and tracing. So I think this is an easy implementation to do until you don't mess up. Simple thing or a simple way to mess up this implementation if I don't go through all the layers of my application. So let's say if I'm having a separate health check that's happening at the HTTP layer, I should forward it to my original controller. Even better, go through with an HTTP forward to the original controller, and just don't try to mess up in a lower layer. Because if my circuit breaker implementation is usually at the controller part of the MVC, I'm not going to be able to be in sync with circuit breaker setup. Okay, so now with deep hash checks, with probing, especially with probing, I say that we are going to be able to capture most of these issues. Okay, now with passive hash checks, what I'm trying to do, and this is, I think, the most advanced but the most complicated kind of hash check implementation, is that I'm just going to report some kind of statistics of the existing requests and responses. So if I have a metric library in my application that's already providing metrics, it's easier to use their data to tell something about the healthiness of the service itself. And unfortunately, I haven't seen any default implementations. I have my own implementation, but of course, without any kind of guarantee that it's going to work just fine for you. Um, some of the load balancers have this set up already, for example, Envoy. Some of them, unfortunately, not. So what's important in this implementation is that you should not eject one of your instance for forever in the future. So there should be some safety mechanism that's immediately reporting the instance as healthy if some time passed. Another important thing is that I'm providing again a failure ratio, but this failure ratio should just ignore older values. So it should be valid for a certain specific period, like 5 minutes, because just for a failure in the past, I just don't want to eject one of the instances for forever in the future. As I said in Envoy, there is this thing called outlier detection. This is the simplest setup possible. In this example, it says that for every consecutive 500 HTTP responses of 3 responses, I'm going to just give a break to that instance. Again, there is a base ejection time that tells it what's the maximum duration for removing the instance itself. There is a max ejection percent that tells that only 50% of the instances should be just removed. So if there's kind of configuration issue or something similar, it doesn't make sense again to remove all of the instances at once. That's why there is a safety mechanism also built in here. Okay, good thing is that Envoy provides pretty good statistics about the outlier detection. You can see that now there's a plateau at 50%, again, because it doesn't make sense to eject all the instances, because that was my setting. And this is how a similar graph can be provided by Prometheus, and what you can use, for instance, for configuring your own alerts based on the outlier detection by Envoy. So I say with passive health check, um, because it works by real transactions, you are going to again able to capture all of the issues at once. That's the good news. And you don't have to bother with synchronizing with other patterns like circuit breakers or defaults, fallbacks, or local caching when it's still providing some values. Your configurations will be as simple as I say practically possible. And now it's time for some demo, because I think it makes sense to also show the practical side of all these theories. In the demo application, this is what I was setting up. So if you go at my code base in GitHub, um, the whole thing is being able to fire it up with the simple make command in Docker Compose. Um, you're going to have two load balancers. You can compare them to each other. I'm going to show you different kind of metrics from Envoy and Traffic. I used Quarkus for the service implementation. For the health check implementation, I used microprofile health um, specification based implementation, and I'm using MongoDB. So let's have a little bit of discussion of how this looks for real. Um, First of all, let's see how the health check looks by default. What I think is a wise thing to do is to introduce feature flag for each and every kind of health check. So when you have any issues, you can just disable, enable them, and then restart or redeploy your application. Of course, as I said, there is an aggregated health check by default that's showing up all of them. This used for backward compatibility, but I think it's also useful for other situations as well. And um, there is a shallow health check available as the liveness probe, which just shows the disk healthiness. and there is a readiness probe available which tries to show up more by the database connection. So now I disable the probing and metering health check, and let's see what happens if the database is not running. Now everything is up and healthy. I'm going to give break for the database instance. All right, let's check here the health check again. Unfortunately, it required me a lot of time to provide information because I'm using a real request to check if the database is healthy or unhealthy. It's going to be the same with probing health check. So let's just turn back the database. You can see that with the probing health check, it's trying to do a real transaction. I'm trying to return a real data as the response. Um, with the cost of again some synthetic request. So I have a simple implementation that tries to increment a counter here, and I'm incrementing the counter also with the hash check itself. So if I go and try to retrieve the data for real from another endpoint, the counter is also here increased. So that's the cost of having probing hash check. It provides more realistic data, but unfortunately of the cost of having also submitting real requests that has to be filtered out. Again, if I just stop the database itself, it's going to have the problem of the timeout. It's going to be more slow than it should be. Now with the passive health check, the good thing is that this this cost does not necessarily needs to be paid. So again, let's go back to the deep health check here, because that's where I included, I think, the passive health check. But let's see, here's the metering health check. It's now enabled. That's a good thing. Maybe I have not turned off the probing health check. That's right. That's why it's still slow. All right. Now my application is up and running. I have these metering health check turned on, which is also showing that okay, there's no issue here. As soon as I'm trying to, let's say, again, retrieve some data from the application itself, but fail because I provide real metrics in the application, it immediately reports that, let me zoom this in, it immediately reports that now the application is not able to provide any information, but it does not require to wait for the timeout because it's based on existing statistics. I will show it again after some requests. All right, again, you don't have to pay for the timeout. You can see here a failure ratio. If you are interested, I won't go into details. You can find this implementation that I did in my GitHub repository, which includes the sandbox. And again, an important feature is that after a certain period of time, which is 20 seconds in our case, it will again report itself as up and running, even though the failure ratio is higher, because it does not make sense to remove an instance forever. So when I'm going to go back and enable the database itself, everything gets back to normal. Again, you can see that the ratio will drop. The metering health check should just simply after 20%, it's still 31. Okay, let me just provide some more. After 20%, it should still report the application is up and healthy. Okay, now let's talk a little bit about the metrics themselves, the alerts themselves, and how it should look in a real dashboard. So, um, if you want to experiment around the sandbox, you are going to be able to have different kind of experiment based on your current setup. Um, in the chaos testing folder, there are some shell scripts we've just which will just for a period going to kill and then start a specific random container. It will do the same with pods as well. If you are running Kubernetes or Minikube, you can run an end-to-end test. So that's what I did as an experiment in the certain time period that you can see on the screen. And I have variable interval here. So let's talk about the failure rate itself. So this failure rate shows um, some suspicious spiky outages. But as soon as let's change the interval to 5 minutes, it's going to disappear. So here in the alerts are not configurable, unfortunately. Um, so what I'm going to do here is that I'm going to edit them and set the same period. You can see that everything's flattened. But the truth is that there were some spiky outages happening, and you can see that because it was um, related to a dependency, the database, this also caused a response time increase and some rate drops. So the rate immediately dropped to the timeout, which was 5 seconds. So I was able to just provide one response per 5 seconds. But because we were able to provide more data, more successful requests in the previous period before these outages, that's why it's not shown here. So again, this can be an advantage or a disadvantage. If you don't want to share or show um, some kind of short outages, you can just hide them by choosing a longer interval. All right. In this cluster healthiness, you can see that the good thing is that it's working even though I haven't had traffic for all the time. These periods which have zero healthy instances were the same when the database was not running. These were the most dangerous ones. This is the same period. If I go back and show the 1 minute interval, was the same period when we had the same spikes. You can also investigate the outlier, the statistics of the outlier detection for Envoy, and this is the query for doing that. You can see again here that the maximum is 50% all of the time. Most of the time we've detected some kind of issue, so most of the time one of the instances were out. This was because of the um, um, high period of removing and then putting back the instances. Okay, I don't have so much time left, but I might be able to show you one example, last example related to deployments, because that was also what I promised to do. So let's say that I have the deep health check enabled, which will also verify if my connection is working properly. Let's say that I messed up the database configuration. Okay, and I'm trying to go out into production, roll out this change to production. Now what you can see here that I have a Kubernetes cluster up and running, application is up and healthy. Also it's available here in the application itself, or let's show up some real transactions. I'm able to get some real transactions, but I have an issue in the configuration. So when I try to, let's increase the version for the um, instance that I'm going to deploy. just release 1.1. This should stop the deployment, and I should be able to just go back and roll back my implementation. Okay, and that's, I think, the last example. So when this is finished, I'm up to some Q&A for the rest of the time. I hope the deployment will end up relatively soon. If not, I will just abort and leave it for you for experimenting. So because, just a little explanation what's happening here. So because I have the startup probe that just have the aggregated health check of everything that's implemented here. Because in the new version I have the MongoDB health check enabled, but the wrong configuration, it should just show up my instance as being unhealthy. And startup probe should just not go ahead and roll out the deployment until the application is not reporting itself as healthy. This helps me avoid configuration issues. Good thing is that I'm still able to get some information from the old instances or from the old versions. Okay, so this won't affect my availability at all. But we block the deployments. So what I'm simply just going to do, I have to take a little bit of hint here. I'm just going to undo my rollout. Okay, with this simple comment here. Yeah, and after short period, everything should be back to normal without any kind of outages of the service. I'm still able to get responses. But now I still have the old version. The number of posts just increased for a while, but it's going to be lowered and then just going to be back to normal. I have still the two instances. Okay. So I think that was it. Thank you very much. Thank you for being here. And I'm looking at the YouTube chat, hoping that you have some interesting questions here. I need to wait until the stream buffering gets to that point at the end of my presentation. So I will wait. If you have any questions afterwards, just don't hesitate to contact me, okay, by the given information in the last slide. Just send me a direct message or find me on LinkedIn and just start the chat if you have any questions. All right. I don't think that we have any questions today, so thanks so much for being here and for listening. There's going to be, oh, sorry, there was just a question appeared. Which health check pattern would you use if you can only use one health check? That's a tough question, Peter. Um, I would say that based on my experience, the metering health check or the passive health check provides the most information from the running service, but it's also the most difficult to get it right. So what would I suggest to you is to go with something simple. Let's say um, go for the default deep health check if that's possible. That also includes the database pool configuration and try to improve based on that. So probably the next step or the next level would be doing synthetic health checks or probing if you are onto other fault tolerant patterns. If your application won't evolve so much and won't have other fault tolerant patterns introduced, then you probably have to stop at deep health check. It does not matter how many health check implementations you have. You can have multiple ones, as I have in my sandbox. It's important to have also a feature flag. It's very easy to add, and you can just turn off your feature flag whenever you want. For example, if you are using Spring Boot, you have everything as default. So you have the connection pool by default, or that you can use the disk healthiness, the HTTP pool, and you can just turn them on, turn them off based on your needs. If you have AWS managed database, you can set up alerting, let's say at database level. You might not necessarily need deep health check, and you might just decide to go out and use the HTTP pool healthiness. In brief, I think that's it. But if you have additional questions, just find me and let's have a conversation. Okay, so thank you very much again. Thank you for being here. I think the time's up, unfortunately. So please stay at this channel because there will be many other interesting presentations, not just me. And again, thanks for watching. Have a nice day, everyone. Have a nice evening. Bye bye.